Into previous modules, we discussed classification of the plasmas and a difference between low pressure plasmas and atmospheric pressure plasmas. What is important if we have collision-dominated plasmas, which are typical example of plasmas at atmospheric pressure, we can define application area for collision plasmas based on type of collisions what we are looking for. Among different collisions are collisions between ions and neutrals, and those are very effective in momentum transfer. And because of this efficiency to transfer momentum, we can use them to control the flow. So basically we can generate a plasma in the flow, and we can control direction of the flow, we can control the speed of the flow, and that we can do without use of any mechanical parts. Then also there are collisions between ionic species which are generated in the plasma. And those collisions are very effective for the charge transfer. We can create ions in the plasma. Those ions can be used to charge the particles, and this is typically done in the electrical precipitators where dusty particles are charged by the use of plasma, and then can be collected with applying positive or negative potential depending on the charge of the particles. We also have collisions between electrons and neutrals, and they are typically very efficient for dissociation and ultra-fast heating. That heating happens much faster than typically achieved by any other means and can be used for flame stabilization. The last kind of collisions are collisions between not two particles but between three particles, what we call three-body collisions or multi-body collisions. An example of applications of the plasma which is dominated by three-body collisions is formation of XMRs. XMRs are particles which are formed, for instance, by interaction of electrons with xenon, forming excited state of xenon. That excited state of xenon atom will interact with two atoms of xenon, forming what is called XMR, xenon 2 excited. That particle has very short lifetime and will very fast be destroyed, forming photons of UV emission. And so plasma, where XMRs are produced, can be used as a very efficient source of radiation with UV light in very deep UV range. And overall, in all plasmas which are collision dominated, we will have multiple collisions between electrons, between ions, between neutrals, and what is important there, we will have dissociation of the particles, excitation of the particles, and will be multiple particles formed there, and many of them will be chemically active. And so plasma itself can be considered as a reactor where we produce chemically active media. So we are forming some kind of non-thermal chemical reactor full of electrons, ions, excited states, and basically that can be used to drive various chemical processes. And with this, we can use plasma for electrification of the industry. The heavy industries such as steel, cement, glass, and production of chemicals is one of the hardest sectors to carbonize, and it's responsible for about 30% of the global CO2 emission. And the core challenge is to reach high temperature. Many processes would require 1,000 up to 3,000 degrees Celsius, and traditionally it is achieved by burning fossil fuel. Why this is so CO2 demanding process, and it's why producing so much of a greenhouse gas. To decarbonize fully, we need technologies that could effectively convert renewable electricity into controllable heat. And the plasma is one of the most promising solutions. Why does it matter so much for industry? Because it can be directly used to transfer electrical energy to thermal energy. Secondly, it can be precisely controlled and very flexible. Depending on the amount of energy which is currently available from renewable sources, we can switch on plasma, we can switch it off, we can reduce power what we introduce in the plasma, and plasma almost immediately on the scale of nanoseconds will respond to the amount of power which is introduced, and so it will be very flexible in operation. On the top of that, plasma is not only producer of the heat, it also has a lot of additional components. Energetic electrons and radicals, they can break strong molecular bonds and drive endothermic reactions, and so they can enable electrified chemical pathways. Also, plasma very often replace fossil fuel burners in existing furnaces and reactors and will minimize the design accelerating of deployment. And all of this can be achieved with no combustion of fossil fuel. So there will be no emission of greenhouses, and so all processes which are plasma based can be powered by renewable electricity enabling truly carbon-free processes. So, overall, plasma offers a powerful road to electrify high-temperature industrial processes and eliminate fossil fuel dependence. By converting renewable electricity directly into intensive heat and reactive environments, it enables clear production, new chemical pathways, and significant emission reduction. And with continued innovation and deployment, plasma could become a cornerstone of full electrified near zero industrial future.